Hello again. We are now on to we are still in the into topic of vector spaces, but today what we're going to do is look at a concept, sort of an idea that is more general than just vector spaces. It can be used in vector spaces, function spaces, and it's what's called Gram-Schmidt orthogonalization, or as I put it down here, how to construct an orthonormal basis. And you will find this discussed in Riley, Hobson, and Bence in on page 275 in section 8.13.1. So we have skipped quite a bit now to get to this point, and because of that, I'm going to take a bit more care explaining this to you, because these ideas are central to actually using the inner product which we've defined in the last couple of tutorials, and using the inner product to construct an orthonormal basis. So here's what we are going to do. Let's say you're working in a two-dimensional space here, and you've been given some basis for this space. Now it's a two-dimensional space, so there are at the most two linearly independent vectors possible in this space. But there could be an infinite number of pairs of these vectors, but this is one such pair. And I've drawn them of different lengths, and they are clearly linearly independent, meaning you can't express E1 in terms of E2 or vice versa. But they are also not orthogonal, are they? I mean, so what we'd like to do is to make their lengths equal and equal to 1, and we'd like to make them orthogonal. So we'd like to make these perpendicular in an no, I'm not talking of perpendicular in the sense of 90 degrees, but perpendicular in a more abstract sense. Now, what does that mean to us? It means that we need to have the norm. So just to remind you, the norm of a vector with itself is given by the square root. So the norm of A is written like this. This is the norm, and this norm is the square root of the inner product of A with itself, and this is the length. Yeah, so this is what we would look at traditionally as the length of A. So what we want here is that the norm, or in this case the square of the norm, but it doesn't matter when it's equal to 1, the inner product of E1 with itself is equal to 1 as the inner product of E2 with itself, and this is why we give this orthonormal basis this hat. And this hat signifies that this is a special basis. It has been made, all the vectors in this basis have a length 1, and they are mutually orthogonal. So the orthogonality comes in here in the second line. The inner product of any vector with another vector is 0. Now this can be summarized using the Kronecker delta. This is the Kronecker delta, delta ij. And what we say very simply is that the inner product of EI with EJ in the Dirac bracket notation is equal to delta ij, and delta ij is equal to 1 if I is equal to j, that gives us the first line, or 0 if I is not equal to j, and that gives us the second line. Okay? The question now is, given a basis like this, how do we construct one like this? So let's see how it's going to work. The very first thing I'd like to do is to understand what the inner product means. So let's take a vector A in some n-dimensional space. Now we know that we can write A if I'm given a basis of this space. So this is my space, and it has a basis EI. This is an ordinary, unnormalized, non-orthogonalized basis, and this is n dimensions. Okay, so we can write this vector A in terms of this basis as follows. The sum I goes from 1 to n is the dimension of the space. Then we will have what we call our components of A along each of these basis vectors. And this is how we write a vector in terms of a basis, and this is something you know from from just any vector x written in terms of I, j, k, etc. And you've seen this before. Now what I'd like to do now is use the Dirac notation for what I'm for the duration of this tutorial. In the Dirac notation, a vector is written either in the bra or ket form, and we normally use the bra form, sorry, the ket form. This would be written as follows. So that's the vector A, just 1/2 of the Dirac bracket notation. This is the bracket notation, and that's equal to the sum I is 1 to n, ai is a constant, and then we have the basis vector ei in there. All right. Okay. Now using the Dirac notation, as you'll see, it just ensures that I don't make any mistakes, and that's why he invented it. In fact, it's a nice, compact, useful notation for many purposes. Okay. Now what I'd like to motivate is that ai is the component of the vector A along this vector EI. So let's see how we see this. One second. Well, I made a mistake over here. What I'd like to do is to use an orthonormal basis. So let me see if I can erase that part, and we make this an orthonormal basis, like the I, J, K basis sets, basis vectors you've been used to. So now let's take the inner product of A with EI. Now since A is the ket, what I have to do effectively is as follows. I'm going to take the inner product, so EJ hat with A. Now we'll go back to black. So EJ hat comes in on the bra side. I'm taking the inner product of EJ hat with the vector A, and that will mean I take, we have an EJ hat. Let's use a different color here. With all this stuff over here. So that's in black. Okay. Now let's see what we know is going to happen here. And on the ket side, we've got a linear combination of different vectors. If you wish, you could put a parenthesis around this, just to remind us that this is one vector, which is the linear combination of different basis vectors. And on the bra side, we've got one vector here. Now we can use axiom 2 of our definition of an inner product, and if you're not sure what it is, please go back to Riley, Hobson and Bence and have a look at the axioms of the definition of the inner product, or look at my previous recordings on this topic. And axiom 2 lets us pull the sum out of the inner product. So this can be written as the sum I goes from 1 to n. Now because these scalars ai are in the ket side, they will not get complex conjugated. They get pulled out as they are. And what we are left with then is, let me keep using a different color for E hat j bar ei. Okay. Now because this is an orthonormal basis, what I know from here is that this is going to be equal to a delta ij or delta ji, but it does not matter. And if you're not sure why it doesn't matter, please think about it or ask me about it in the tutorial. Alright, so this then is equal to the sum I goes from 1 to n ai delta ji. Now I'd like you to think about how do we handle a delta, a Kronecker delta function, Kronecker delta, sorry. Remember, it forces its indices to be equal, so I is equal to j. and it collapses one sum. Basically, j is not a dummy index, right? Because j is on the left, and therefore it must also be on the right. I is summed over. So in this sum, I takes all kinds of values, and when I is equal to j, we get a 1 from the Kronecker delta. And for all other values of I, we will get a 0 from the Kronecker delta. So the only term which contributes to the sum is the term for which I is equal to j. And effectively what this Kronecker delta has done is to set I is equal to j and to collapse the sum to give us just one term, the term for which I is equal to j, and that gives us aj. Alright, so therefore what we can see from here is that aj is E hat j a. And we know that aj is the component of the vector a along this vector ei, or ej in this case. Therefore, we must interpret this inner product of the vector, of the basis vector, the orthonormal basis vector ej with a, as the component of a, of the vector a along the basis vector ej. Now this is going to be important for what I'm going to do next. Alright, so now we are ready to do Gram-Schmidt orthogonalization. Let's take a basis now of just two vectors. These two vectors are e1, and it's not normalized, and e2, also not normalized. And these are a basis of two, so they are not linearly independent. Sorry, they are linearly independent, but they are not necessarily normalized or orthogonal. And what we want to do is to find out how do we get to this basis of orthonormal basis vectors. So let's start with e1. Basically, you pick any one of these vectors from this set. I'm going to pick e1 because, well, it's 1, yeah? But it doesn't matter which one you pick at the start. And I'll show you how this works with an example. For now, let's just look at this in the abstract sense. So we pick e1. Sorry, it's not a unit vector. We pick the vector e1. And if I have only one vector in my set, then all I need to do is to normalize it. And once I normalize it, then it becomes a vector of unit length. So let's do that. So if I wanted to create a normalized form of e1, I want to create this. Then what I should do is take the vector e1 and divide it by its length. And its length is the norm, which is written like this. Or if I wished, we could write the norm in terms of the square root of e1, the inner product of e1 with itself. Okay, so that way we get a normalized vector e1. Okay, that sounds fine. Graphically, what we've done is we have taken some vector e1, and we have converted it into, we've kept the direction the same, we've just converted it into a normalized vector e1. Now let's take the second vector in this set. e2. Alright, now if we did the same for e2, we would create a normalized e2. Well, it wouldn't mean that e2 is perpendicular to e1. Let's take the example I had at the start. If I simply took e2 and I made it normalized, it would still be in this kind of funny direction, and it wouldn't be perpendicular to e1. So we've got to remove that part of e2 which is along e1. Let me show you what I mean by this. So let's draw this thing out. this is, oh, that's not what I wanted. This is our nice normalized E1 hat, and E2 is, that's not what I wanted this. E2 is this vector I've got here. Now you can decompose E2 into a part that is, let's see if I can do this. Well, I'm not sure how to do that, so let's just, we can decompose E2 into a part that is orthogonal to E1 and a part that is in the direction of E1. I should make this a little shorter. There. E2 is equal to the sum of these two vectors. Now what I want to do is, I don't want this part which is in the direction of E1, and I want to keep only the part that's orthogonal to E1. So how do we do this? Well, I know how to find out which part of E2 is along E1 hat, and that's given by the inner product of E1 hat with E2. If I take the inner product of E1 hat with the vector E2, I will get the component of E2 which is along E1 hat. So this thing here is E1 hat, the inner product of E1 hat with the vector E2. That's the component of E2 that is along E1 hat. So what I'm going to do now is as follows. We're going to take the vector E2 as it is. I'm going to subtract out, and this is where the Dirac notation comes in handy. So let's use the Dirac notation here. I'm going to subtract out that vector. I'm going to leave a bit of space there. That amount now this amount of E2 is along E1 hat, therefore I must add E1 hat here. So let's have a look at this. This is E2, the vector E2. This is the amount of E2 that is along E1 hat. So when I subtract out E2 minus this component which is along this direction, what I'm left with is something that must be perpendicular to E1 hat, because that amount of E2 that was along E1 hat is now being subtracted away. So this part I now know is perpendicular to E1 hat, but it's not yet normalized. So what we need to do then is divide it by, if I call this vector A, just for, I have to divide this, let's write it separately. If I call that vector A, then E2 hat is equal to A divided by the norm of A. And this vector E2 will be perpendicular to the vector E1 hat. And it's also normalized. And this can be generalized, but before going to the generalization, let's see how this works in practice. Oh, by the way, before moving on, why did I use the Dirac notation in the first place? I should have used the Dirac notation here too. It's this. This combination of a ket and a bra in this order occurs very frequently when we take when we define a projection. Basically what I'm doing here is taking E2, projecting it onto the vector E1 hat and subtracting off that from E2. And because this combination occurs so often, I prefer to use the Dirac notation when writing down the Gram-Schmidt formula. It helps me remember where does E1 hat go. Is it in the bra side or in the ket side? And it's always in the bra side that it goes because of this form. Now this might seem like a little detail. It will make sense later. For now, just accept it for as it is. So let's see an example before we actually go to generalize this. So the example I'm going to be using is E1 is equal to 1, 0, and E2 is equal to 1, 1. Now when you're faced with a choice like this, have a look at the vectors and see if you can pick one which is we could, as I said, you could start with E1 or you could start with E2 as your first vector. But we know that E1 is already in the right form. It's already, in fact, it's normalized, as we shall see, and it has the form of a vector along the x-axis. So let's start with E1. Now let's see what our procedure says. The procedure says that we start with E1, and then to create E1 hat, we take E1, the vector, and divide it by its norm. So let's find the norm of E1. Well, the norm is given as the square root of the inner product of E1 with itself. So let's have a look at, now I'm doing this in steps. In practice you will skip steps, but let's do everything properly now. So what is the inner product of E1 with itself? Well, that's given by the sum, in this case I goes from 1 to 2 because it's a two-dimensional space, of the components of E1. So it's going to be E1, the vector, the ith component, star E1, the vector, the ith component. Okay, now let's apply it. So this would be, in I is 1, we get a 1, so it's 1 times 1, and the star doesn't do anything in this case because these are real vectors. So it's 1 times 1, I'll put the star in any case, plus, when I is 2, you will get 0, so that's 0 star dot 0, that's equal to 1. In other words, this is already, so that's equal to 1 from here, and therefore this is simply equal to 1, 0. Okay, so that part was easy. Now let's see what we can do with E2. Our formula says that we are going to have to first define this vector A, which is E2 minus, let's have a look at this thing here, minus E1, the vector E1, and then the inner product of E1 hat with E2. So yeah, let me be precise. It's minus E1 hat, the vector E1 hat, not E1. And the inner product of E1 hat with E2. Let's use the Dirac notation just as a reminder that this is what we are up to. And that's going to be, the vector E2 is, so let's evaluate the components before we put them in. So we need the inner product of E1 hat with E2. And that's going to be E1 hat. So we use the same formula we had before. I'll show you how to do this more quickly, but for now let's just use the formula. I goes from 1 to 2, E1 hat, and the ith component of that starred, and then E2 ith component. And that's going to be, so I is 1, it's going to be 1 star times 1, so that's 1 star times 1, plus, when I is 2, it's 0 star times 1, and that's equal to 1. So what we end up here with is the vector 1, 0, sorry, 1, 1, that's E2, let's just remind me, E2 is the vector 1, 1 minus E1 hat. Now what does the vector E1 hat look like? It's 1, 0. And this inner product is 1. So that's equal to the vector 1, 1 minus 1 times this is simply the same thing. And that's equal to 1 minus 1 and 1 minus 0. And that's equal to 0, 1. So that's the vector A. And now to complete this, I need to normalize A. So I need to find out what the norm of A is. Now you can already see what this is going to be. I'm going to leave it as an exercise to show you that, show this. And that allows us to write E2 hat as A divided by the norm of A, which is equal to the vector, so 1 over 1, that's the norm, and the vector 0, 1, and that's simply the vector 0, 1. So to put it down together, therefore the orthonormal basis is E1 hat, which is equal to 1, 0, comma E2 hat, which is equal to 0, 1, exactly as you would have expected. No surprises there. That's what you would have expected. Now, how do you generalize the Gram-Schmidt? So okay, for this we're going to keep using the Dirac notation. Generalization works as follows. So let's put it down again. E1 hat is equal to the vector E1 divided by the norm of E1. And we'll use Dirac all the way. E2 hat is equal to the vector E2 minus E1 hat. E1 hat, that's the first thing I write down, and then we have the vector E2 coming in. And then we have to divide it by the norm of everything above. I'm just going to write this as the numerator. So you divide it by the norm of the numerator. E3, what do you think is going to happen here? Well, E3 will have a component along E1 and E2. So we need to subtract both those components out. So the vector E3 subtract the component of E3 which is along E1, subtract the component of E3 which is along E2, oops, divided by the norm of the numerator. And this can go on. I'm not going to bore you with what happens next, but this can be generalized to any number of vectors. It just follows the same procedure. And in this way we can take a basis of n, linearly independent vectors and create an orthonormal basis of n vectors, which is much more useful for many purposes than a set of any linearly independent vectors. Alright, so that's Gram-Schmidt orthogonalization. There will be problems on this in the quizzes and in the homework sets, so make sure you've understood it. And any questions you have, of course, we'll tackle them in the tutorial session. Thank you for watching.